Relax. Enjoy your coffee.
Okay, so after sitting around and drinking my coffee and scratching my head a little bit, I thought I'd clarify a little bit more about foil shapes specifically. Now I've got this foil I've cut in half here. This is a foil with the thick point 20% back and 16% thick. This is your more standard surfboard fin off the shelf. They're about 6% thick, and the thick points, well, it's around 30%, but often they go flat in the middle here for a fair while, which is of no real purpose. By that I mean you should always be varying your curve, otherwise if you're just sitting flat for a long time, it's not adding or removing anything from a foil's performance. And this one here, the thick point here is 30% back, and what I'm going to do is put these in a water flow, which we don't need any complex testing equipment, we just need the garden hose, and I'll vary the water flow a little bit, but essentially it's probably about the speed of surfing, because surfing's a really slow sport most of the time in most waves around the world until you get over 5 or 6 foot. Then the speed picks up a bit. So let's get to it. So we can really see with a standard surfboard fin, which of course has a flat inside and a rounded outside, totally asymmetrical foil, but with a sharp leading edge. You'll notice that this is extremely sharp, like most surfboard fins. And most surfboard fins are toe in towards the nose, so the water's actually intersecting at about, not straight, but a bit in, and you can see what happens when you run a sharp edge toe in even slightly. So if you slightly turn, that's what's happening underwater with your foil. You can see if it's on the other side, it actually laminates around the foil flow, but it's such a shallow fin, it's only 6% or something, it comes off really quickly. Whereas if you grab the 16% thick, you can see that it handles a much higher angle before it actually delaminates off the back of the foil, or after the thick point of the foil. This is a 20%, this is still 16% thick, but the thick point is 20% back from the leading edge, and this one's 30, so I've increased the water flow speed a fair bit. So with a 20% back fin, you can see that, I have to do it the other way, you can see that the water snaps off the thickest point part of the foil earlier than the 30% fin, which it really, you see it really stays on a lot longer. It doesn't get thrown off. So we've got 4 things to consider there. There's the leading edge shape, the thickness of the foil, how far back the thickness is from the leading edge, and then the cavitation or lamination factor. So starting with the leading edge, if you have a sharp leading edge and the angle's not exactly perfect, you'll have the water break off from the leading edge, which just causes cavitation or airspace down the side of the fin. The thickness of the foil, it'll govern how much lift you get, but also somewhat govern the maximum angle of attack. If you have a very thin foil, your angle of attack, that meaning the angle of the fin, this is the water flow, and the angle of the fin that we varied, that you saw in the previous footage. The shallower fin, the thinner fin, definitely couldn't handle as high angle. It really cavitated much earlier. And when you get this, when you're taking off, especially on a steep wave, if you don't have lamination to the side of the fin, you will spin out. It's not even a question. It just won't handle as well. And then if you do control it by managing the rail, you have to wait a lot longer before the fins re-grab with a thinner fin. That thickness really allows a massive angle of attack range. The thin fins like this, the fat fins like this, and you can really get out of sticky situations. The thickness point towards the leading edge, or how far back it is from the leading edge, that will help you from a standstill. So it'll actually increase the angle of attack even more, and it'll get you going very quickly, especially from if you've ended up in a strange angle, or you've done a bottom turn or a cut back and you've effectively stalled. You can start more quickly. The downside is that once you get up to speed, you'll have the water breaking off behind the thick point more easily, because the entry angle is sharper. So it depends on what you want to achieve as to whether you have that thick point further forward or further back. Most of the NACA and NASA airfoils floated around the 30% mark, but you also got to remember that aeroplanes are travelling at in excess of 180 kilometres an hour, and we're lucky if we're hitting 50 or 60. On a big wave you might hit 80, but you'll know about it when you're doing 80 k's an hour, because that's exceptionally fast. And then it's only, unless it's really big, it's not really for that long. Most of us, however, we're starting and stopping with cutbacks and bottom turns, so we're stalling a lot. On lamination and cavitation, the water breaks off the fin. It either does two things. It either breaks off the fin, causing an air pocket, or it cavitates by pulling air in from somewhere else. Now, if the water pressure lowers up near your board, it will suck air down the side of the fin if there's an air space that happens, which often does if there's a slight piece of chop. The other thing that happens is the water will turn from liquid to air once the pressure gets low enough. It's based on the ideal gas law, but if you watch, an easy way to see it is to watch footage of a fin underwater, or just watch fish in an aquarium. You'll notice they have little bubbles on the tips of their fins, and that's because at some point the water gets depressurized to the point that it changes phase from liquid into gas. And once that happens, then you've got all other sort of turbulent situations happening. It's especially noticeable in fins, and on large ships you actually get it when the gas turns back into a liquid. It often impacts behind the leading edge of the fin, and it eats into the steel of a large ship's prop. When I say large ship, I'm talking in excess of 30,000 tonnes, and we're nowhere near that with surfing. But it is a factor. People will argue that water is a non-compressible flow, but even though it's non-compressible, the force still remains. And yes, it doesn't compress anymore, but does decompress back to a gas. So the force between the atoms is important to think about. So even though most people just want to go surfing and they don't really care about the science behind all of this, the key point here is that the thing that people think affects the performance of their fins is not the main ingredient. Most people think that the profile, the outline shape that they can see visibly is what affects the performance of their fins mostly. And I'd probably put it down to 25-30% of the overall difference that it makes. The other 70-75% is in your foil shapes. So even though you may not understand or care to understand about all the things I've been talking about in the last 10 minutes, you can see through those fluid flow tests just with the garden hose and 3 fins that I've got on this video that it does make a difference. The fins you buy will not tell you how thick the foil is. It's not written on it the percentage thickness, how far back it is from the leading edge. They don't talk about a leading edge radius. They don't talk about foil shapes all the way down the fin. You need to get yourself a set of calipers and start writing those things down, or just having a look and remembering what the proportions are. So look at the proportions of those foil shapes as they progress down your fin, and think about those shapes relative to other fins, and start trying some thicker fins. And don't believe anything I'm saying, just go test it for yourself, and you'll see that there is a significant difference in foil shapes. And it actually does, if your overall profile shape is more or less the same between 3 or 4 different fins, you'll see that the foil shapes make a bigger difference than you think.